So let's look at mutually exclusive and the union of two events. So two events A and B from the same sample space are mutually exclusive when A and B have no outcomes in common. In the terminology of sets, the intersection of A and B is the empty set. So here this is showing the intersection of A and B. There's nothing that they have in common. Okay, so it could be anything like this, right here. So you could maybe have like all of the hearts and the diamonds here, and then all of the spades and clubs here, for example. So there's nothing intersecting. There's red cards versus the black cards. So there's nothing they have in common. The probability of the union of two events, if A and B are events in the same sample space, then the probability of A or B occurring is given by the probability of the union of B equals the probability of A plus the probability of B minus that intersection. Now, if they're mutually exclusive, so they have nothing in common, then you're just going to add the two probabilities together. Now, something that overlaps, say, for example, and we'll see it in a little bit, has to do with cards. So it says, what's the probability of drawing a heart and the probability of drawing like a face card. And so some of them overlap. So we'll see those examples next. So you draw one card at random from a standard deck of 52 playing cards. What's the probability that the card is either a heart or a face card? So just like the example I was stating. So a heart, we know the probability of a heart. So there are, number one, 52 playing cards, right? So hearts, there are 13 hearts. And then the probability of a face card, there's 3 cards in each suit. So 3 times 4, there are 12 face cards out of 52. But there are also heart cards that are also face cards, right? So there are 3 cards out of 52 that are heart and face cards. So what we're going to have to do is we're going to take the probability of the heart plus the probability of a face card minus that intersection, the probability of a heart and face of 3 over 52. So this is 13 plus 12 minus 3 over 52. So that's going to be 22 over 52, or 11 out of 26, and that is approximately 0.423. So try the next example. You draw one card at random from a standard deck of 52 playing cards. What's the probability that the card is either an ace or a spade? So probability of an ace is 4 out of 52. The probability of a spade is 13 out of 52. Now the probability that it's a spade and an ace, that is 1 out of 52 chance. So it's 4 plus 13 minus 1 all over 52. That ends up being 16 out of 52. Or if you reduce it, 4 out of 13. So therefore that's approximately 0.308. Let's look at the probability of mutually exclusive events. So here's a table here. The Human Resources Department of a company has compiled data showing the number of years of service for each employee. The table shows the results. What's the probability that an employee chosen at random has 4 or fewer years of service? So first you need to total the number of employees here. So we just total this all up, and just to kind of help us out, that total is 498. So the probability that an employee has 4 or fewer years of service, we're looking at this. So therefore, it's going to be 157 over 498, which is approximately 0.135. Now, what's the probability that an employee chosen at random has 9 or fewer years of service? So we are going to take these two right here, so 157 plus 89 over the total of 498. And so that is going to be approximately 0.494. So you're just taking all of these numbers here. There's no overlapping. All right, so this is just the probability of A plus the probability of B. There is no intersection. So in example 8, what's the probability that an employee chosen at random has 30 or more years of service? So that's going to be 35 over 498, and then that's approximately 0.070. Let's look at the probability of independent events. If A and B are independent events, then the probability that both A and B will occur is a probability of A and B, which is and then you're multiplying, right? So it says and, then the probability of A times the probability of B. So a random number generator selects 3 integers from 1 to 20. What's the probability that all 3 numbers are less than or equal to 5? So it's very important to be careful to read this, less than or equal to 5. So less than or equal to 5. So it can be 5, 4, 3, 2, and 1. So the probability of choosing a number that is 1 through 5 is 5 out of 20 numbers, which is 1 out of 4. And so we're choosing 3 numbers. So we're looking at 1/4 times a fourth times a fourth, or 1/4 to the third power, which is 1 out of 64, which is approximately 0.016. So try this example here. A random number generator selects 2 integers from 1 to 30. What's the probability that both numbers are less than 12? So the probability that they're less than 12, so you're saying 1 through 11. So that's probability of the event is 11 out of the sample space of 30. And so we're choosing 2 numbers, so probability of A times the probability of B. So really we're just looking at 11 over 30 squared. And so that's 121 out of 900. So that's approximately 0.134. Let's look at the probability of independent events here, another one. In 2015, approximately 65% of Americans expected much of the workforce to be automated within 50 years. In a survey, researchers selected 10 people at random from the population. What is the probability that all 10 people expected much of the workforce to be automated within 50 years? So the probability of A is at 65%, right, chose that or think that it's going to be automated. So what that's going to be, so it has to be, each person picks that. So it's 65. So if we pick 10, that all 10 are chosen. So the probability of A is really raised to the 10th power. So it's 0.65 to the 10th power. And so that is going to be 0.013. So try this example here. In example 10, researchers selected 5 people at random from the population. What's the probability that all 5 people expected much of the workforce to be automated within 50 years? So again, the probability of choosing a person that expects that is 65%. So that probability to the 5th power. And so that's 0.65 times 5, right? Because it's each time you're choosing that person, 65% chance you're going to choose someone. Okay, so that's why it's to the 5th power. So when you do that, 0.65 to the 5th power is 0.116.